Let's examine the following series. The sum as k goes from 1 to infinity. Negative 1 to the k plus 1 times 1 over k. And let's evaluate some of the terms. So that's a series, since we're adding them all up. The sequence that defines it, a sub k, is negative 1 to the k plus 1 times 1 over k. Let me ask you this question first. What is the limit as k goes to infinity of a sub k? What will that be? Well, the answer, of course, is 0. 1 over k gets smaller and smaller as k gets large. 1 over 100, 1 over 1,000, 1 over 1,000,000. That part's going to 0. In this negative 1 to the k plus 1, what is that doing? That's just alternating between positive 1 and negative 1 as we move along. So to kind of get an idea where this is headed, let's take a look at some values. So here's k. Here's a sub k. We're starting at 1. Negative 1 to the k plus 1. It'd be negative 1 to the 1 plus 1. Negative 1 to the 2. Positive 1 times 1 over 1 will give me positive 1. If I go to 2, negative 1 to the 2 plus 1, that is going to be negative 1 to the 3rd, or negative 1 times 1 over 2. That's going to give me negative 1/2. Going to 3, you'll notice that we're now moving back to positive 1. Negative 1 to the 3 plus 1 times 1 over 3. So negative 1 to the 4th is positive 1 times 1/3 is positive 1/3. And maybe you can see the pattern as it's heading this way. So next would be what? Negative 1/4. Then 5 would be positive 1/6, etc. So those are our values as we go. But we're interested in what the sum would be. So we have to take a look at our partial sums to see where they are. So we could take a look at that. So let's see if we can identify what some of our partial sums would be for this. So this time we're going to look at n. And this time we're going to look at s sub n, which is the same as the sum as k goes from 1 to n of negative 1 to the k plus 1 times 1 over k. So if n is 1, we're going from 1 to 1. That, of course, is just 1. If n is 2, it's 1 minus 1/2. If n is 3, it's 1 minus 1/2 plus 1/3. We get the idea. And what would 4 be? 1 minus 1/2 plus 1/3 minus 1/4. So let's quickly get some approximations for these things. So this, of course, is 1. 1 minus 1/2 is 0.5. Next one, 1 minus 1/2 plus 1/3 gives me about 0.8333. And then if we subtract 1/4 from that, we get 0.58333. So again, these are the partial sums. So do we think this is going to converge, or do we think this is going to diverge based on these numbers? Let's jump to a spreadsheet so we can do this a little bit more quickly. So here's some of the numbers I have. Notice the 1, 0.5, 0.833, 0.5833. And continuing down through 21, we're at 0.716. And let's see if we can go a whole lot beyond. Does this seem to stabilize? Certainly seems to be stabilizing around 0.690879, somewhere in that neighborhood. So it appears to me as if the limit as n goes to infinity of the s of n. Remember, that's what we're dealing with here. These are partial sums. These are not elements of the series. Remember, my series was alternating. These are the partial sums. The partial sums seem to be converging to something in the 0.69 area. We could do a few more if you're interested. See how long it'll take for us to get a 3rd or 4th decimal point of accuracy. Where are we at here? 692, 694, So we're at 500. We're still not quite at 3 decimal places of accuracy, but we'll do a few more. Whoops. And we'll see if we can get it to stabilize. But again, it certainly appears to be converging, but taking its time doing that. So we'll do a few more. You get it for free. That's one advantage of spreadsheets. It can do the computation for us quickly. Where are we at? 0.6925, 0.6937. So yes, it certainly seems to be that these things are going to converge. And indeed it does. But the question I want to ask you is looking at this. This is alternating. So let's remove the sign flasher for a minute and just look at this thing. The sum as k goes from 1 to infinity of 1 over k. Does that converge or does that diverge? What happens to that one? And the answer is it diverges, right? That is our harmonic series. That's our harmonic series. So it diverges very, very slowly, but it never stabilizes. But by putting the sign flasher in, that thing does converge. So how can that be? What's our issue here? What are we going to talk about? Well, we're going to use something called the alternating series test. So what does the alternating series test tell? So we're going to start with a series that's always positive. So let a sub k be greater than 0. And eventually we'll relax that to just eventually positive. But for the most part, for the alternating series we study, the a sub k will be a sequence of positive elements. Now, how do we make that alternate? We add a sign flasher to it. So we look at something like this. K goes from 1 to infinity of -1 to the k. Or equivalently, it could be the sum as k goes from 1 to infinity of -1 to the k plus 1. The difference between these two things is that -1 to the k, this starts out negative, then is positive, then is negative, then it's positive. This one starts positive, and then is negative, and then is positive, and then is negative. But they're both alternating series. So a sub k is always positive. The -1 to the k or -1 to the k plus 1, I call a sign flasher. It alternates positive, negative, positive, negative, positive, negative. This will converge when what happens? This converges when the limit as k goes to infinity of a sub k equals 0 and a sub k decreases. So what do I mean by the fact that a sub k, again, looking at the positive part without the sign flasher, that decreases? That means the next term is always less than the one that came before that. So what that means is that means a k plus 1 is always less than a sub k. So what I often say here is I say a sub k decreases to 0. That's the symbol that I use. So it heads towards 0. The limit is 0, but it does that in a decreasing fashion. If that happens, then this version of it will indeed converge. The sum of that alternating series will be a convergent one. Another way to look at this, if I have, for example, the following, if I'm looking at the sum as k goes from 1 to infinity of -1 to the k plus 1 times 1 over k, that's the example we just looked at. Let me go ahead and call that sequence b sub k. So b sub k is -1 to the k plus 1 times 1 over k. It follows the requirements, right? The 1 over k part is always bigger than 0, and it has a sign flasher. And then what I do is to remove the sign flasher, I look at the absolute value of b sub k. That removes the sign flasher. That, of course, is just 1 over k. What can we say about that? That decreases to 0. It goes to 0 in a decreasing fashion, 1/2, 1/3, 1/4, 1/5. That decreases to 0. So we could say the absolute value of b sub k decreases to 0. Therefore, the sum of b sub k converges by the alternating series test. The sum as k goes from 1 to infinity of b sub k, which equals the sum as k goes from 1 to infinity of negative 1 to the k plus 1 times 1 over k converges. So that's another way that I have to think about this. So to look at a second version of defining the alternating series test. Alternating series test. If b sub k alternates, again, which means it goes from -1, negative, positive, negative, positive, negative, positive, negative, positive, negative, positive, right? Then we can argue that the sum as k goes from 1 to infinity of b sub k converges when what happens? When the absolute values of b sub k, removing the sign flasher when that shrinks to 0. This is going to be our issue. So let's take a look at another one of these relevant to what we're talking about. Let's look at the sum as k goes from 1 to infinity. This time I'll start with a negative number, -1 to the k times 3 over the square root of k. So if we wanted to look at some values, we could. What is a sub 1? -1 to the 1 times 3 over root 1, which of course would be -3. A sub 2 would be -1 to the 2nd times 3 over root 2, which is positive 3 over root 2. And a sub 3 would be -1 to the 3rd times 3 over root 3, which is -3 over root 3. You get the idea in terms of how this works. So what do we ask ourselves? Well, if we remove the sign flasher, so again, what do we have? We have, we'll call it, I guess I called it a sub k here instead of b sub k. A sub k is -1 to the k times 3 over the square root of k. The absolute value of a sub k removes the sign flasher. That's 3 over the square root of k. Now, what is the limit of that as k goes to infinity? What is the limit as k goes to infinity of 3 over root k? Well, that certainly is going to be 0. As k gets large, 3 over square root of a large number is going to be 3 over a large number, which is going to tend to 0. And then the question is, does it decrease? Well, I think that's obvious. As the bottom gets bigger, the entire thing shrinks. So I would be okay with you saying that it decreases. Just making that statement, say 3 over root k decreases. So the conclusion then would be what? Conclusion is that our original series, the sum as k goes from 1 to infinity of -1 to the k times 3 over root k converges by alternating series test. If you want to prove that that decreases in a little bit more sophisticated fashion, AST, alternating series test, you take the derivative, right? To prove that a function decreases, take its derivative. If the derivative is negative, it's a decreasing function. So just a second look at that. What I have is I have the absolute value of a sub k equals 3 over the square root of k. I'm interested in the limit. Check that. I'm looking at the derivative of that. So we'll say f of x is 3 over the square root of x. Show f of x is decreasing. Can I do that? Sure. What's the derivative? So f of x is 3x to the -1/2. What is f prime of x? 3 times negative 1/2 x to the negative 3/2. So f prime of x is negative 3/2 times 1 over x to the 3/2, which is always less than 0. So if f prime of x is less than 0 for all positive x, certainly greater than 1 if you want, because this is where this is defined, then we can say absolute value of a sub k, which equals 3 over root k, is decreasing, right? When k is greater than 1. But again, I don't think that's really necessary, because 3 over root k, again, as the denominator gets bigger, the fraction gets smaller. We can see that it decreases. We can see that its limit is 0. Those are the two conditions that I need to prove that an alternating series converges using the alternating series test. Okay. Now, let's take a look at another one. The sum, as k goes from 1 to infinity, we want it to alternate. Negative 1, we'll make this one to the k plus 1 times k over 5k plus 3. So let me ask you this question. Does this series converge according to the alternating series test? Does it converge according to the alternating series test? Yes or no? Well, let's think about it. My a sub k, I'll call it b sub k this time, is alternating. Negative 1 to the k plus 1 tells me it alternates. K over 5k plus 3. But if we look at the absolute value, so that it removes the sign flasher, then I get k over 5k plus 3. And what are the conditions that I need? What must be true for an alternating series to converge? What do we need? Well, I need two things. I need the limit to be 0, and I need it to be decreasing once I remove the sign flasher. But what is the limit as k goes to infinity of the absolute value of b sub k? It's the limit as k goes to infinity of k over 5k plus 3, which if you want to use L'Hopital, you can, although certainly Calc 1 strategies work as well. Limit is x goes to infinity of x over 5x plus 3. Take the derivative of the top, derivative of the bottom. Limit as x goes to infinity of 1 over 5, which is 1/5, which is not 0. That is not 0, so the alternating series test does not apply here. Remember, the two things we needed, the absolute values had to have a limit of 0, and it had to get there in a decreasing fashion. That doesn't happen here. The limit here is not 0. So I cannot make an argument that the series converges. But I want to show you something. We're going to take a look at the statement of the alternating series test in a textbook. And I want to make a point here that is often missed by students. Okay, so here we go. Here's our definition. They're using n's instead of k's. I prefer k's. I like to use n's for partial sums. But you get the idea that the a sub n part, the non-alternating part, the limit has to be 0, and a sub n plus 1 has to be less than a sub n. It's decreasing. So those are the things we meet. But that's if. It is not if and only if. And it is not ever telling us anything about whether the series diverges. So if I want to conclude that this series diverges, I have to think of another strategy that I could do, that I could use, and the series does indeed diverge. So what would be the most efficient way to prove that? So our goal here is to say the sum as k goes from 1 to infinity of negative 1 to the k plus 1 times k over 5k plus 3 diverges. And how should we prove that? So what would be the best way to prove that this thing diverges? So make your selection, think about that. Best way to prove that this thing diverges? Well, b sub k is negative 1 to the k plus 1 times k over 5k plus 3. I'm going to look at the kth term divergence test. What is the limit as k goes to infinity of b sub k? That is the limit as k goes to infinity of negative 1 to the k plus 1 times k over 5k plus 3. So let me ask you to answer that question. What will that limit be? What will that limit be? What does it tell us? Well, we know this part gets closer and closer to 1/5, but this alternates between negative and positive. So what's happening here goes essentially for way out, the numbers are close to 1/5 and close to negative 1/5 and close to 1/5 and close to negative 1/5 and close to 1/5 and close to negative 1/5. It never stabilizes. So the limit does not exist. I can't say that the limit equals 1/5. The limit of the absolute values does, but the limit of this thing does not exist. So our conclusion then is the sum of the b sub k, which is the sum as k goes from 1 to infinity of negative 1 to the k plus 1 times k over 5k plus 3 diverges by the kth term divergence test. Okay, and next I want to look at the sum as k goes from 1 to infinity of negative 1 to the k minus 1. Notice that still is going to be a sign flasher times k over 3 to the k. So we'll call b sub k that, and this part is always positive, which it has to be. So b sub k is negative 1 to the k minus 1 times k over 3 to the k. The absolute value of b sub k removes the sign flasher. So that's k over 3 to the k. Now I need to show goal, right? Goal. This alternates. I have an alternating series. I want to show that b sub k decreases to 0. So I've got to show that its limit is 0, and I have to show that it's decreasing. Now, showing that its limit is 0 is going to be a game for L'Hopital. Showing it's decreasing is going to be a little trickier. So let's do the limit part first. What is the limit as k goes to infinity of absolute value of b sub k, which is limit as x goes to infinity of x over 3 to the x, which gives me infinity over infinity. So L'Hopital is okay. So I take the derivative of the top and the bottom. The limit is x goes to infinity of what? The derivative with respect to x of x, the derivative with respect to x of 3 to the x is the limit as x goes to infinity of 1 over 3 to the x times the natural log of 3, which equals 0. So we get that part. without too much trouble. Now, how can I show that it's decreasing? That's going to take a little bit more work. So what I want to do is I want to examine the next term divided by the previous term. Remember, our goal to show that it's decreasing, I want to show that b sub k plus 1, or absolute value of b sub k plus 1, is always going to be less than or equal to, but it will be less than, the absolute value of b sub k. So equivalently, what can I show? Equivalently, if I divide both sides by absolute value of b sub k, as long as it's never 0, it would be equivalent to saying the absolute value of b sub k plus 1 divided by the absolute value of b sub k is less than 1. If I can show that, that's sufficient to show that it's decreasing. So my absolute value of b sub k here is this. I'm going to approach it this way to try to show that it's decreasing again. Two things I need to show for alternating series test. The limit is 0, and it's getting there in a decreasing fashion. So take a look at that. Absolute value of b sub k equals k over 3 to the k. Absolute value of b sub k plus 1 is k plus 1 over 3 to the k plus 1. I want to show it's decreasing. Again, you could have just used a derivative, shown that the derivative is negative eventually, then it is decreasing. But I believe this will be a quicker strategy for us to approach. So remember, I want to show that the next term divided by the previous term is less than 1 to show me that this is a decreasing sequence. The next one, b sub k plus 1 divided by the previous one, b sub k. Again, removing the sign flashers, that's why I just call it the absolute value. K plus 1 over 3 to the k plus 1 divided by k over 3 to the k. What does that give me? K plus 1 over 3 to the k plus 1 times 3 to the k over k. Now 3 to the k over 3 to the k plus 1 gives me a 3 downstairs. So I have k plus 1 over k times 1/3. You can look at various values, right? What do you get? Here's k, and here's 1/3, k plus 1 over k. If k is 1, 1 plus 1 is 2, 2 over 1 times 1/3 is 2/3. If k is 2, 2 plus 1 is 3. So it's 1/3 times 3 over 2, which is 1/2. If it's 3, what do we get? 3 plus 1 is 4/3. 1/3 times 4/3, which is 4/9. All of these will be less than 1. You see how this is behaving, right? That's heading to 1 times 1/3. This is always less than 1. I think that's obvious. So we can conclude that we can conclude that the absolute value of b sub k plus 1 is less than the absolute value of b sub k, since the next divided by the previous is less than 1. So the sequence is decreasing once we remove the sign flashers. The sequence is decreasing. And we said that the limit was 0, also showed previously that the limit as k goes to infinity of the absolute value of b sub k equals 0. So what do we finish with? We finish by saying then the sum as k goes from 1 to infinity of -1 to the k minus 1 times k over 3 to the k converges by the alternating series test. Now let's see what it converges to. It's not going to be a nice number. It's going to be something we're going to have to work with, a decimal approximation. So let's jump to Wolfram alpha and see what we get. So we're going to take the sum of what? -1 to the k minus 1 this time, of k over 3 to the k. Okay, over 3 to the k. Let's look at some partial sums. How about k goes from 1 to 10? What do we get? Around 0.187. K goes from 1 to 100. About 0.187. Wow, there's a whole bunch of nines. So maybe this does converge to something nice. Maybe it is 0.1875. Interesting. We can go from there. So it's not quite a geometric series, but it's certainly close. It's similar. Wow. Look at all those nines. Well, that's kind of fascinating in terms of how that worked. Okay. So indeed, that series does converge by the alternating series test, and we saw the number that it's getting fairly close to.